This video covers the material that you're supposed to know from GCSE Physics in order to take A-level physics. If you're really stuck, then try this book. It covers all the stuff you need to know and it's mildly entertaining. It comes with a health warning. There is a unit error on page 6, but apart from that, it's good. Most of us meet electrical charge as quite young kids. You get people do silly tricks at parties, like rub a balloon on their jumper and then stick it to the wall by magic, or seeing people's hair stand on end because they've been charged with a Van de Graaff generator. Static electricity is a really strong force. We now call those two flavours of charge positive and negative, and you're supposed to know that like charges repel. These two balloons have been charged with friction charging wool onto the balloons. They are repelling each other. Electrostatics experiments are notoriously unreliable. When I tried polishing the blue balloon with a polyester duster and the red balloon with a piece of wool, they also repelled each other, which is not what's supposed to happen. But fortunately, my red balloon had this really big attraction going for the backdrop to my video. So we do have an example of electrostatic attraction, just not the one I hope to show you. Electrical charge is measured in coulomb, which is named after Charles Augustin de Coulomb. 1 coulomb is the charge that moves past a point if a current of 1 amp flows for 1 second. The modern idea of electrical charge is that the charge is quantized into particles that we call electrons, that Greek word for amber. The symbol for this is lowercase e. As far as we know, electrons can't be subdivided any further. They don't have any internal structure that we can detect. The charge on one electron is minus 1.6 times 10 to the minus 19 coulombs. So that's really small. It's also the size of the charge on a proton, although they have a positive charge. Handily, this means that almost all atoms in the universe are electrically neutral, and that's quite a good thing. Electrical charge is a strong force. If you're studying the Welsh or Eduqas exams, you need a handle of the size of the charge in an electron compared to a full coulomb. And I've tried to find a pair of ratios that gave you the same relationship. According to Wikipedia, the area of the whole island of Great Britain, that's the main island, so the bits that are covered in grey paper on this map, like Ireland and Harris and Lewis, are not included in that figure. That area is 229,848 times 10 to the 6 metres squared. And the area of a penny is 3.2 times 10 to the minus 4 metres squared. I tried to compare that to the charge on an electron and then 1 coulomb, and it turns out that the ratio electron over coulomb is 8,810 times smaller than the two areas. The thickness of a modern steel penny is 1.65 millimetres. If you stacked up 8,810 pennies, you'd get a stack about 14.5 metres high. So if you imagine that stack of pennies right across the whole island of Great Britain, then the area of all those pennies, if you spread it all out, compared to 1 penny, would be the same ratio, different quantity, same ratio, of the one charge on 1 electron to 1 coulomb. 14.5 metres is about the length of an articulated truck. So if you're trundling up the roads of Britain, bored on a journey one day, and you think this journey's going on for a long time, imagine all those Arctic trucks stacked on end, piles of pennies as deep as they are, right across the whole of your boring journey, and that's the same ratio, area of penny to area of all of those pennies, as 1 coulomb to 1 electron. If you want a dollop of charge, you can go to the supermarket and buy some. You buy a battery or a cell. Good quality cells tell you the amount of charge that they can hold. They have it printed on them. Rechargeables usually do. And if you buy from an electronics catalogues, their better quality batteries will tell you the amount of charge they hold. They use a unit either of amp hour or milliamp hour for little chargers. Things like van batteries and truck batteries give you the charge held in amp hours. You can get asked loads of questions about this. They're not really full, proper A-level questions, but they might be the sort of questions that they ask at the beginning of a long question, just to sort of warm you up a bit. So you get things like, you can work out how much charge does this AA cell store? And it turns out that my 2,900 milliamp hour batteries hold 10,440 coulomb, which is an awful lot actually. The van starter motor draws a current of 200 amps. How long can this battery deliver this current? Time is charge over current, and it comes out to 1,980 seconds, which is about 33 minutes. A pair of these AA cells will run my GPS for about 10 hours. So what current are they going to draw? And again, you use the current equation, and it comes out to about 0.29 of an amp. But I don't quite believe that. That seems like a really big number. So I'm going to measure the current, and I've used this setup to do so. What I've done is take the batteries out of the GPS and put them in an external battery box, so I can put the ammeter in series with the GPS. And you need all the charge to flow through the ammeter, so all those little electrons get counted as they go. Large currents are really dangerous, and they will happily kill ammeters, so it's good practice when you use an ammeter, start on the biggest current range and turn the ammeter down until you get a sensible reading. The current here is 5 microamps. This is loads lower than my calculated value. I think this is for various reasons, mostly because actually the electronics in the GPS are quite voltage sensitive, and they shut down when the voltage from the batteries drops below a certain threshold. This introduces the idea of voltage. If you have to explain voltage to a little kid, then you describe it as something like the push that makes charges move, so something like this toy can work. And little kids cotton on pretty quickly that if they don't have batteries in a battery-powered toy, or the batteries die, so does their toy. At A-level, you're required to come up with a bit of a more sophisticated picture. You're expected to know that the voltage source is the energy source in the circuit. You can get that energy from mains power or our friends, the batteries. The other components in the circuit, they're all called transducers. They are designed to convert that energy from the electrical energy delivered by the cell or the main socket into other forms, so light, sound, heat. The unit to measure this energy transfer is the volt, and it's named after a bloke called Alessandro Volta. 1 volt is 1 joule per coulomb of charge. A lot of specifications say you've got to remember this, so set it to the tune of Wheels on the Bus, sing it, and you'll remember it forever and ever and ever. Measure voltage by putting a voltmeter in parallel with the thing that we want to measure, because we're measuring the energy difference between 2 points in the circuit. In this first illustration, I'm measuring the battery voltage, so I've got my voltmeter in parallel with the battery. It's measuring at 2.86 volts. The energy drops across the useful components in the circuit can be measured by putting voltmeters in parallel with them. We've got here a change in energy, and the energy comes about because of the position of the component in the circuit. So energy from position, that's potential energy. So the voltage drop across a component is called the potential difference, the energy lost because that component converts it to another form. You can see here I'm measuring a total voltage of 2.487 volts. This is similar to the battery voltage, but actually it's not exactly the same. I confess to leaving the lights and the circuit switched on while doing photography, faffing about, so I've flattened my batteries a bit. Voltages here are different because the 2 lamps have different power ratings, and this photo shows the 2 lamps with no other photographic lighting, and you can see one is clearly brighter than the other. This photograph shows me using 2 multimeters. The one on the left is being used as an ohm meter to measure the resistance on the right, which is being used as a voltmeter. Voltmeters typically have very high resistance so that they don't provide an alternative route for the charge to move through, and they don't disturb the circuit that they're trying to read. You can see here that this ohm meter is reading about 1 mega ohm. That's actually quite small for a voltmeter. Typically the voltmeters you use in a classroom, digital ones, will be about 10 mega ohm. Ohm meters measure resistance by driving a very small current through the thing that they're trying to measure, and for this reason it's quite important, if you're using one, you make sure it's switched off when you've finished, because if you leave a multimeter on the ohm meter setting, when you come back to use it again, the internal battery will have died. Another energy source is from a generator, like this bicycle dynamo, which is rated at 6 volts and 3 watts. And you might get asked questions about these things, like if it runs for 10 minutes, how much charge has moved and how much energy has it converted. You need to use the power equation from GCSE to work out the current running through this thing. So power is current times voltage is the special form that works for DC circuits. Actually, the derivation of this and more on electrical power comes in a later video, so I'm going to sort of skirt over this bit. But you can find that the current is about half an amp, and then substitute that into the equation for charge is current times time to find that the charge being moved in 10 minutes here is 30 coulomb. Remember to convert your minutes into seconds. Final thing is that you can work out the energy using charge times voltage, and the energy change here is about 180 joules. Resistance. The definition of resistance is voltage over current, but this is not Ohm's law. Ohm's law has an extra clause about temperature and comes into a later video where we talk about why resistance is and factors that affect resistance. Total resistance in a circuit is sometimes called the load that the cell or the power supply has to drive. For this instance, it's really easy to calculate, and because our current is 0.23 amps and the voltage is 2.21 volts. The resistance of a particular conductor depends on its shape, its size, and the material properties it's made from, environmental properties as well. The unit for resistance is the ohm, and it's named after George Simon Ohm, and this is his picture. Some specifications, notably the Advancing Physics spec, also use conductance. This is the reciprocal of resistance, so it's either current over voltage or 1 over resistance. Wikipedia offers lots and lots of alternative units for conductance, but actually the A-level one is Siemens with an S on the end. SI units are never plural, but Ernst Werner von Siemens has an S on the end of his name. He founded the technology company that's still in business today. This video covers the underpinning ideas from GCSE Physics that you're supposed to know for A-level.